So far, we've considered operators in which we're concerned with only one kind of particle. That is, we've been considering either identical bosons or identical fermions. Many important phenomena involve interactions of different kinds of particles. Examples include the interactions of photons, or phonons, the quanta of vibrations, with electrons. To extend to this case, we need two additions. First, we must include the description of the occupied single particle states for each different particle in the overall description of the states. Second, we need commutation relations between operators corresponding to different kinds of particles. Let's look at the states first then. In considering the occupation number basis states, for example, for a system with two different kinds of particles, we simply have to list which single particle states or modes are occupied for each different kind of particle. Suppose then that we have a set of identical electrons and a set of identical bosons, such as photons.
For a state with one fermion in fermion state, or single particle state to be more precise about it, K, and one in single particle state, Q, and, for example, one photon in photon mode, lambda d, and 3 in photon mode, lambda s, we could write the state in a list form. So here we have our one fermion in fermion single particle state K, and one in single particle state Q, and here we have one photon in photon mode lambda d, and here we have 3 photons in photon mode lambda s. We could also write that in this notation, which we'll come back to in a minute. Or alternatively, we could write this state out using creation operators acting on the empty state. So that would be this notation here. So here we have our empty state. Here we have 3 creation operators for photon mode lambda s. Here we have 1 creation operator for photon mode lambda d. We have a fermion creation operator for fermion single particle state Q, and a fermion creation operator for fermion single particle state K. We have this 1 over root 3 factorial here from this use of 3 creation operators, and we previously deduced that we had to have that in there in order that this would produce a normalized state. So in this notation we've just written down for this state, we could say that NFM is the mth possible list of occupied fermion states. That is, we imagine we could write down all sorts of lists of occupations of different fermion states, and we could give those an index, which we could call M, and this would just be one particular one of the possible lists of occupied fermion states we could write down. So that list here is this list as in the cat here. And similarly, NBN is the nth, little n, possible list of occupied boson states. So here it's this list corresponding to this list up here. Note now that this empty state here is one that is empty both of this kind of fermion and this kind of boson. We now postulate that creation and annihilation operators for different particles commute under all conditions. Specifically for the boson and fermion operators, we would have this kind of relation. So this is a commutation relation, even though these are fermion operators. We're saying that operators for different particles, creation operators, will commute with one another. So this is the creation operator for fermion single particle state J, the creation operator for boson mode lambda, and similarly over here, and we're saying that those will commute. It won't matter which order we create these different particles. It will make no difference to the state. Similarly, here is the one for the annihilation operators for those states and modes. And we're also saying that the annihilation and creation operators for different particles commute. So here is the creation operator for fermion single particle state J, the annihilation operator for boson mode lambda. and similarly the other way around. Note that similar relations also would hold for annihilation and creation operators corresponding to two different kinds of fermions, such as electrons and protons.